Welcome to Peshawar Model School, Nashara campus. Don't forget to subscribe our YouTube channel so you will watch our upcoming videos. Hello students, hope you will be fine. Today we will discuss our 11th lecture from class 10 chemistry, unit number 9, chemical equilibrium. As we have learned a lot in this chapter about the chemical equilibrium, that what is chemical equilibrium, how we can establish the chemical equilibrium, what are the irreversible and reversible reactions, what are forward and backward reactions, what are the conditions for the equilibrium, and what is the law of mass action, and many other topics. But today we will do the revision of all the topics in the short term just to recall your memory and knowledge. So in this way we can check out ourselves that how much we have learned in our previous lectures. Okay, so now let's come to the main points. Let us look at your book, page number 17. These are the key points which we are going to discuss one by one in the short term, just to recall your knowledge, as we have learned these points in detail in our previous lecture. So in this lecture we will summarize all the topics in the short way. So our first point is the irreversible reactions. What are irreversible reactions? Those reactions in which the products do not recombine to form the reactants are called irreversible reactions. Let us look at this reaction. In this reaction, when hydrogen react with the oxygen gas, it will give us 2 moles of water molecules. So you can see that these two reactants are reacting together and give us the product, but this product do not recombine to form the reactants in the backward direction. So we can represent these reactions by the single arrow, and the single arrow proceed from left to right in the irreversible reaction. Let us look at this common example. When we burn the wood in the presence of oxygen, it gives us carbon dioxide and water vapor, and at the end we got only the coal, but we can't react that coal and can't get the wood in the backward direction. Means that these reactions are somewhat we can call the physical changes. So we can say that this example, the example of the wood and the coal, is the physical changes. So irreversible reactions are somewhat called the physical changes, because in the physical changes we can't go in the backward direction in any reaction. The second one is the reversible reactions. What are the reversible reactions? Those reactions in which the product can react to form the reactants again are called the reversible reactions. Let us look at this example. In this example, here 3 moles of hydrogen react with 1 mole of nitrogen gas, and at the end it will give us 2 moles of ammonia gas. So in this case these products will react back and will give us 3 moles of hydrogen and 1 mole of nitrogen in the backward direction. These reactions can be represented by the 2 arrows. The first one arrow is from left to right, so it will be for the forward reaction, and the second one is from right to left, so it will be for the backward reaction. These reactions do not reach to completion. What does it mean by this? It means that this reaction doesn't go to completion, means that at this stage the reaction is not to be completed, because this product react back and will give us hydrogen and nitrogen in the backward direction. at the same rate at the same time. Let us look at this simplest way for the explanation of reversible reaction. Here you can see that at this point the rate of forward or backward reactions will be equal at the same time. So this is what we can call the reversible reactions. The third one point is the equilibrium state. In equilibrium state, the rate of forward reaction will be equal to the rate of backward reaction, and the concentration of reactants and products will be remain constant. Here you can see this graph. In this graph, at the forward direction, when hydrogen and iodine react together, it will give us 2 moles of hydrogen iodide in the forward direction. But this reaction does not go to the completion. It means that this hydrogen iodide will react back at the same rate and will give us the hydrogen and iodine in the reverse direction. So this is the point at which the rate of forward and the rate of reverse reaction will be equal. So at this point we can say that there must be established the dynamic equilibrium, or we can say this is the equilibrium state. The fourth one is the forward reaction. What is the forward reaction? The conversion of reactant into product per unit time, or the rate of chemical reaction taking place in forward direction, is called the forward reactions. Let us look at this reaction. Here you can see that when we give heat to this water molecule, it will evaporate and will give us the gaseous water vapors. So it changed from the liquid phase to the vapor phase. So this is the forward reaction because it proceeds from left to right. So this is the forward reaction. The next one is the backward reaction. What are the backward reactions? The conversion of products back into reactants per unit time is called the backward reaction, or we can say the rate of chemical reaction taking place in backward direction is called the backward reaction. Let us look at this reaction. Here you can see the water vapors which are formed in the forward reaction will react back in the backward direction and will give us the water molecules in the liquid phase. So what are the phenomena behind this reaction? There are two phenomena behind this reaction. One is the evaporation and the other is the condensation. In the evaporation, at the start when we give heat to the water molecule will separate from each other and will goes up to the top of the closed container. But after some time, that water vapors will condense back to the bottom of the container. So that is the condensation. So there must become a point or the state at which the rate of evaporation will be equal to the rate of condensation. So that point will be the equilibrium point, or we can say that there must be established the chemical equilibrium. Okay, the next one is the law of mass action. What has been stated this law? This law stated that the rate of chemical reaction is directly proportional to the product of the molar concentration or the active masses of the reacting substances. What does it mean by this? It means that any chemical reaction or rate depend on the molar concentration of any reacting substance. Means that if the moles of any reacting substances are higher, so the rate of that chemical reaction will be higher or the faster, or the speed of that chemical reaction will be faster. But if there are less mole of the reacting substances, so automatically the speed of that chemical reaction will be lower, because This directly proportional sign means that if one component increasing, so automatically the other component will also be increasing, and if the one component decreasing, so the other one will also be decreasing. The law of mass action was proposed by two Norwegian chemists, Cato Gullberg and Peter Wake. Cato Maximilian Gullberg from 1836 to 1902 and the Peter Wake from 1833 to 1900. They proposed this law as a general description of the equilibrium condition after observing many chemical reactions, because it gives a relation between the concentrations of reactants and products at equilibrium in any chemical reactions. Means anyone can find out the concentration of reactants and products through this law in any chemical reaction at the equilibrium stage. Active masses. Active mass means the concentration of reactants and products in mole per decimeter cube for a dilute solution. It means that in any molar solution or a dilute solution of any salt or sugar solution, how much concentration of salt or sugar we are taking. So that concentration is actually the active mass of that dilute solution. Means that if we are making the salt solution or sugar solution, so for that molar solution, how much moles of salt or sugar we are taking to make that dilute solution, so that will be in mole per decimeter cube, and these active masses will be expressed in terms of square brackets. These square brackets shows the active masses of any reactant or product, and in the mid of these brackets we will put the reactants or the products. The next one is the equilibrium constant. The product of the equilibrium concentration of the product divided by the equilibrium concentration of the reactants, with each concentration term raised to the power equal to the coefficients of the substance in the balanced equation. It can be represented by Kc or Keq, K equilibrium. Here you can see that equilibrium constant expression or the equation for the equilibrium constant. We can say that it is the ratio of the mathematical product of the concentration of the substances formed to the mathematical product of the concentration of the reacting or the reacting substances. Let us look at this reaction. In this reaction we are going to react 3 moles of hydrogen to 1 mole of nitrogen gas and will give us 2 moles of ammonia gas. So for this we will write down the Kc expression. Let us look at this Kc expression for this reaction. Here you can see that here is 2 moles of ammonia gas. So we will put this moles as a coefficient, and 3 moles of hydrogen, so we will put 3 as a subscript for this hydrogen gas, and here is 1 mole of nitrogen, so we will not mention the 1 mole for this nitrogen. So you can see that these square brackets shows the active masses, these shows the reactants or the products, and this coefficient shows the moles of any reacting substance. We can also find the extent of any chemical reaction with the help of the equilibrium constant expression. The extent of chemical reaction depends upon the magnitude of Kc. So, when Kc is very small, it means that the concentration of A and B is large, or we can say the reactants are large in amount and date of products formed is very small. So the equilibrium mixture will contain the reactants mainly and only a small amount of products will be formed. So it means that the reaction does not proceed appreciably in the forward direction, or we can say it will proceed slowly in the forward direction. If we have the Kc large value, so what does it mean by this? It means that the concentration of A and B is small and that of concentration of C and D is large, means the products formed are in large amount. So the equilibrium mixture will consist almost entirely of product. It means that for products are formed in the large amount, so and the reactants will be in the small amount. So this indicates the reaction is completed in the forward direction, means that products are formed completely in the forward direction. If Kc is neither very small nor very large, so it means that the concentration of products and reactants will be very close. It means that will be at the equilibrium stage, at the dynamic equilibrium stage, and the value of Kc for that reaction. Now, how we can recognize the chemical equilibrium? We can recognize the chemical equilibrium through physical processes and the chemical processes. In physical processes, there are further three processes. The first one is polarimetry, refractometry, and the third one is the spectrophotometry. And in the chemical processes, there is the titration. As we have discussed previously in our previous lectures, that how we can find out the equilibrium in any chemical reaction through these processes. So we can find out the extent or and the direction of any chemical reaction through all these processes, means that we can find out the purity of any solution through these processes. In the polarimetry, we can find out the extent of chemical reaction by passing the plane polarized light through any solution. So if that solution is pure, so the polarization will be different from that which is the impure. And the refractometry, we can find out the refractive index of any solution by through the refraction of that solution. And in the spectrophotometry, we can also find out the purity of any solution by using the spectrophotometer. And in the chemical processes, here is a titration. So titration is a chemical processes through which we can also find out the purity of the substance. That this is the process in which we can find the molarity and the molality of any solution. So we can say that these processes are used to predict the extent and the direction of any chemical reaction.